The last force we want to talk about from chapter 6, last thing we're adding into our toolbox for now, is the centripetal force. We had before talked about circular motion, and to move in a circle, there has to be a center-seeking acceleration to bend the trajectory to always be along a circular path. Well, that acceleration is caused by a force. And that net force that points in towards the center of a circle is going to be called the centripetal force. Centripetal force, center seeking. So imagine that we've got like a ball on a string, and the ball is going in a horizontal circle, just for the sake of argument. So you can have uniform circular motion. And say at this instant in time, that is the velocity vector. What we're saying for the circular motion, and what we said before, is that there's an acceleration in towards the center of the circle. So I'm going to call it A subscript C for centripetal acceleration. And if it's uniform circular motion, those two vectors are perpendicular to each other. Okay. Now, accelerations from Newton's second law of motion have to come from a net force. So all we're saying with this idea of a centripetal force is I add up all of the forces acting on an object. That gives me the net force vector, F net. That net force as a vector sum of forces is going to equal the mass times the acceleration. Acceleration is a vector. Now, we're just putting this into the special case that this net force we add up into something. And for circular motion, just moving in a circle, not speeding up, not slowing down, that net force is equal to the centripetal force times the inertia of the object times the acceleration, which is the centripetal acceleration if it's just moving in a circle. Okay. And we had seen before that that centripetal acceleration is as big as v squared over r. So the speed squared divided by the radius of the circle. So all we're doing is taking that knowledge for the centripetal acceleration, plopping it into Newton's second law of motion to get the centripetal force. Now, we had talked about a force of air drag, talked about the two kinds of frictional forces, static friction, kinetic friction in this chapter. The centripetal force is not a fundamental force like that. For the moon going around the Earth, it's the force of gravity that provides the centripetal force. For this example of talking about a ball on a string, it's tension in the string. I could do this with a slinky, and then it is a Hooke's law force or an elastic force that's providing the centripetal force. There's some physical mechanism or other mechanisms acting together that combine to give me a net force that plays the role of the centripetal force. Okay. And if it's uniform circular motion, then from other reasoning, we know how big that force has to be. It has to be mv squared over r. All right. Let's clean this up a bit. And let's try some questions. Which of the following parameters determines how fast you need to swing a bucket of water vertically so that the water in the bucket will not fall out? So does your answer to that depend upon the radius of the swing, mass of the bucket, mass of the water, A and B both, or A and C both? So think about what you think the answer is, and then we will talk about it. Right. It just depends upon the radius. The mass of whatever is going through the circular motion cancels out. And let's see if we can think about why. try to draw a free body diagram for the bucket of water when it's at its highest point. If it is going just fast enough to not fall out, then we have a force of gravity acting down, right, as a vector. And that's all we're going to have in our sum of forces is mg. Okay? And so for this bucket of water to go through a circular arc at the top and none fall out, then the bucket has to be going fast enough for the force of gravity to provide the centripetal force. So we put that into an equation. We're saying that m times g, the weight of the water, the bucket for that matter, is mv squared over r. And what you'll note is inertia on the right-hand side cancels out with a gravitational mass on the left-hand side. And we'll get a result that speed is the radius of the circular path the bucket is on times the acceleration due to gravity square root. That's all it depends on, because inertial mass, as we've seen a few times now, inertial mass cancels out with gravitational mass. All right, let's try another little calculation. Boom, 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 boom. All right, I have an aluminum rod, and it will break when it's put under a tension of 600 newtons or greater. One end of the rod is connected to a motor, and a 12 kilogram spherical object is attached to the other end. When the motor is turned on, the object moves in a horizontal circle with a radius of 6 meters. A pretty big circle. I won't do this in your lab. If the speed of the motor is continually increased, at what speed will the rod break? And you can ignore the mass of the rod for this calculation. It doesn't really add anything insightful. So see if you can go through and calculate what that critical speed is at which the tension pulling on the rod is going to be large enough to make the rod break. Right, and it is 17 meters per second. So let's go through and see if that makes sense with everybody. So again, we're just applying the idea of a centripetal force. So m v squared over r. And that force is provided by the tension in the rod. So that net force pulling in towards the center of the circle is the tension T. And we have a value for that can't be any bigger than 600 newtons. So we can go ahead and solve for what the speed is going to be. We're going to have R is equal to oh, I'm sorry, we're not solving for R. We're solving for speed. Silly, silly, silly. Solving for the speed. We're going to have R times tension. And now it is not the force of gravity that is causing the centripetal force. So the mass does not cancel out. V. All right, so it is a 6 meter radius for the circular path. This tension is 600 newtons. The mass, since we can ignore the mass of the rod, is 12 kilograms. Put all of those things in. That is like the square root of 300, right? Because 6 over 12 is a half, and a half of 600 is 300. And that works out to be 17 meters per second. All right, one more question And this is an important one, connecting circular motion with free body diagrams. So a ride you might be familiar with from the county 4-H fair or whatever fair you have where you live is what's called here a barrel of fun. There's different names for it in different places. Barrel of death is usually a little bit better sell. But the idea is on the ride, you're on the inside of a rotating drum. And once the drum is spinning fast enough, the floor drops out from underneath you. Your feet are not touching anything, and yet you are still safe and enjoying the ride. So for this person in the barrel of fun, she finds herself stuck with her back to the wall. Which of the free body diagrams below shows the forces acting on her? So think about it, talk it over with your physics friends, and then we will go over the answer together. All right, I want to make sure everyone is clear on why it's 1. This is an important question. All right, so first off, let's look at 4. If I take those 3 forces together and I add them up, I will find that the net force in case 4 is equal to 0. If the net force is 0, Newton's first law of motion tells us we move in a straight line. If we move in a straight line, that means we are flying through the ride. We go right through the wall like some sort of ethereal being. That is not plausible. All right, so not 4. Let us observe that 2 and 3 both give you a net force that has a component down. So these are going to be falling to your death. So not a barrel of fun, be a barrel of mess. So not 2, not 3, not 4. So here's the key question, which we've already answered. Do you have a net force that points in towards the center of the rotating drum, or does it push out? Okay. Well, this force is actually coming from the normal force. The wall is pushing you in. The wall can't suck you back. Okay. The wall can only prevent you from passing through it. Okay? It's not going to try to pull you through it. So the one that gives you correct motion in a circle is the one where you have a net force directed in towards the center of the circle. And then even better, so you don't have a horrible accident, your weight is canceled out by a force that points upwards. And so let's just go through and label what all these forces are to make sure we're all in agreement on what's going on. So her weight acts down. That's not a surprise. Okay, you always are going to have weight when you're in a gravitational field. The wall prevents her from passing through the wall and instead goes through circular motion because it exerts a normal force. And then with a normal force, there is a force of static friction. So there's a force of static friction pointing up. And then the force of static friction is big enough to cancel out the weight. Therefore, she doesn't accelerate up or down, but just accelerates in towards the center of the circle to undergo circular motion on the ride.